Welcome back to another video of our course in probability theory. Today the topic is sums of random variables, real valued of course. And this is a topic which was already covered in your course in basic probability theory, most probably. We will have similar things as you did then, and we will also have the so-called Kolmogorov maximal inequality, which we will need in our next video, which is on the strong law of large numbers. Let's get started. So, you will heard of the name convolution. What is a convolution of probability measures? So if you have probability measures on the Borel sigma algebra on R, and we will already know what their product measure is, and the product measure is a measure on R to the n. And you have the very simple map, which maps a vector of n real numbers to their sum. Then the convolution is the image measure of the product measure under this sum function. So like this here. So what does it mean? That means that's the proposition here, the first one. But when you understand what this here means, proposition 8.16 is an easy exercise. So the definition of the convolution means if you have n real valued independent random variables, then the convolution of so that's again an image measure under a sum is the same as the convolution of the image measures. Yeah. And in addition, the characteristic function of the sum is the product of the characteristic functions, and the same for the Laplace transform. Well, first of all, there are two things we have to see. So the first is just the definition. So, the joint distribution is the product measure of these things. So the left-hand side equals this here, and the product measure of the image measures under the image of the sum function here is by definition here the convolution of the measures, which is the right-hand side here. And for the second assertion, the characteristic function of the sum, like this here, is, this here, just by some properties of the exponential function. And we learned that independent random variables are uncorrelated, and functions of independent random variables are also independent. And since x1 to xn are independent, e to the it x1 up to e to the it xn are also independent. And we can use the fact that they're uncorrelated in order to see this here. And the right-hand side is by definition the product of the characteristic functions of the single random variables. So we are done here. Something more exciting maybe. Again, we have a bunch of real valued random variables and their sum. First of all, the probability that the sum converges is either 0 or 1. Why could that be? We had Kolmogorov's 0-1 law. Here it is. Which claims that if you have independent sigma algebras, that the terminal sigma algebra, which was the sigma algebra, which consists of events which do not depend on the first n or so random variables for any n. So that's p-trivial, meaning that probabilities of events within the sigma algebra are either 0 or 1. And when we want to prove this, or the second statement here, all we have to do is to see that the event that we have here is in the terminal sigma algebra. And of course, if you change the first m or so of the random variables, the fact that it converges or not, the first of these mx here, the fact that it converges or not, does not change. So this event here is in the terminal sigma algebra, and therefore probabilities are 0 or 1. And yeah, well, the same applies to the second statement, because, well, dividing by n does not change the argument here. For example, yeah, here's a more formal argument. So y is the limit here, the potential limit is measurable with respect to the terminal sigma algebra. Well, okay, that's the definition here. But, well, that's also true for any m. You can just ignore the first m minus 1 terms, because that divided by n goes to 0 anyway. So the limit is the same here. And this here only depends on random variables from m to infinity. Okay, but that applies to any m. And since this applies to any m, we can also make the intersection for all m. So let us now, after this funny noise, come to Kolmogorov's maximum inequality. Okay. That's an inequality where you bound this probability here. So this is something we want to control, because in applications of this here should converge, or something related to this. And we want to have the probability that the supremum of this thing here is bigger than k. And we can bound this, as it says here, summing all variances and divided by k squared. So it looks a bit similar to the Chebyshev inequality, but it's not actually. So in order not to have to write too much, here is the proof. Without loss of generality, that will happen in several proofs on the next slides. The expectation is 0. Because if it's not 0, we just subtract it, and, well, it's the same. Sn, as always, will be the sum of the first n random variables. And one trick is here, we are going to introduce this t here, which is the first time, let's say, if the index of the x is time, that the sum in absolute value exceeds k. So the sum always stays below k, and if it's for the first time it exceeds k, then t, you have the t here. So t has values in the natural numbers. And that means, what does t less than infinity mean? T less than infinity means that there is some n such that the absolute value of Sn is bigger than k. So this event here is the same as this event here, therefore they also have the same probabilities. And here we are going to do some calculation, and in the end we will have this here is bigger or equal to this here. When n goes to infinity, this here is the sum of the variances in the numerator here. On the right hand side we have k squared, so we multiply this over here, times, well, the probability that t is less or equal than n, for n goes to infinity, since probability measures are continuous, that's the probability that t is finite. So k squared times the probability that t is finite is the same as this here, and that's exactly what we want to prove. So if you read like this, when we're done with this, we are done with the proof. Okay, let's go on with the calculation here. So the sum of the expected values of the squares here? Well, these are actually variances, and sum of variances is variance of the sum because the xk's are independent. And the variance of the sum is the expectation of the sum square because the expectation is 0. So we have this. Then we can say, well, we distinguish or we partition the whole space into all possibilities t can have. T equals k from 1 to infinity, that would be everything. And if we leave out everything behind n, we at most make it smaller. Okay, and this long thing here is a funny way of writing Sn square. So that's sk square, okay. Sn minus sk plus 2sk is Sn plus sk, and Sn plus sk times Sn minus sk is Sn square minus sk square plus sk square equals Sn square. So that's the same. Now I split the expectation in two parts. Sk square I leave here. Here I have Sn minus sk times Sn minus sk, which is a square, which is non-negative. So if I leave that away, I make it at most smaller. And what remains is 2sk times Sn minus sk, which is this. Well, and that's the reason for this inequality here. And well, this here is actually 0. Why is that 0? Because the random variable Sn minus sk is independent of the random variable sk times indicator t equals k. Because this here only depends on random variables xk plus 1 to xn, and sk times t equals k only depends on the random variables x1 till xk. So this here is independent of these two. So they're independent, so they're uncorrelated. And since they're uncorrelated, the expectation of the product equals the product of the expectations. And the expectation of Sn minus sk is 0 because the xk's have expectation 0. So this here goes away. We're staying with this. And well, we again repartition it. K from 1 to n, t equals k gives p that t smaller or equal to n, and sk square on the event that t equals k. So if t equals k, that means sk is bigger than k. So sk square is bigger than k square, like this here. So we can bound this by this on this event, and then we repartition t equals k and sum all this to t is less or equal to n. And we are done with this proof. And we prove this, we use this in the following result. We have independent random variables which all have a variance, and their variances sum. Then these things here converge almost surely. Well, how does it work? Okay, again, expectation is 0 without loss of generality as n equals the sum, and epsilon is bigger than 0. We have here, or we will have two things. First, we prove convergence and probability, and then we argue that the convergence probability actually is an almost sure convergence. Okay, what could proposition 8.18 bring? I mean, okay, here we have the sum of the variances. That's finite. Oops, I'm sorry. So like this here. What does this bring? First of all, that brings the following. If I have the probability that Sn minus Sk is bigger than the epsilon that we just chose, and supreme for all n bigger or equal to k, that's less or equal than, well, according to what we just had. Okay, here I start with 1, now I start somewhere else. But the only thing is I have to also sum the variances of all these which appear here in the supremum. So I have to make a sum over n from k plus 1 to infinity, which are all of these. Expectation xn square divided by epsilon square. And if n goes, if k goes to infinity, k goes to infinity, I mean, we know that the sum here converges, and if the lower limit here goes to infinity, that must converge to 0. And that means that since epsilon was arbitrary, that this supremum here converges to 0. So supremum n bigger or equal than k, Sn minus Sk, goes, as k goes to infinity, to 0 in probability. Well, we know that there is a subsequence. So a subsequence k1, k2, and so on, such that the supremum n bigger or equal than ki, Sn minus Ski, for I goes to infinity, goes almost surely to 0. However, as the supremum here is over fewer and fewer of these random things, which means that this sequence here in the lower bound is decreasing. And if you have a decreasing sequence and you know that some subsequence converges to 0, there's no other chance that the sequence itself goes to 0. So we have that supremum n bigger or equal to k, Sn minus Sk goes, for k goes to infinity, almost surely to 0. Yeah, and that means that we have almost true convergence, because that means here that this sum here of the xk's converge, because we know that there's no chance that Sn minus Sk is really large. Okay, that's it for today, and next time we are going to speak about the strong law of large numbers. Thanks.